In the last video, we talked about the difference between static and dynamic typing and how one trend in static typing is towards increasingly expressive type systems. In this lecture, we're going to talk about self-type, which will give you a taste of what those more expressive type systems can look like. To begin with, let's motivate the problem that self-type solves by looking at a simple class definition. So here we have a class count, and it has a single field I, which is an integer initialized to 0, and it has one method increment. And essentially, the class count just increments a counter. So initially, when you allocate a new count object, the counter is 0, and then every time you call inc, the counter's value is increased by 1. And notice that this can be thought of as a base class that provides counter functionality. So whenever I wanted a counter for some specific purpose, I could define a new subclass and that of count, and that subclass would automatically inherit the inc method, thereby allowing me to have counters without having to re-implement the code. And in this case, the amount of code is very, very small, but in general, you can imagine having a class that implements something tricky or requiring a lot of code, and it's useful to be able to reuse that in subclasses. Now consider a subclass of count that we might want to define called stock. Say we're implementing a warehouse accounting program and we want to keep track of the number of items that are in stock of certain different kinds. So we define a new class stock that inherits from count, and now we'll have a new field in here to make this object, this class, different from its parent. We'll just have a name that corresponds to the name of the item that's in stock. And now down here, we can actually use this. We can allocate a new stock object. So we create a new object. We increment it to indicate that we have one thing in stock, and then we assign it to some variable that we've declared of type stock. And then later on, we can use this A object as we like. Now, the problem is that this code actually will not type check. There is a type error in this code. And why is that? Well, let's think about it for a minute. So what is the signature of inc? So inc, remember, was declared to return things of type count. Right? And when the inc method is inherited by the stock class, this signature doesn't change. It still returns things of type count. So here we have a new stock object. We call the increment method, but the type of this whole thing is a count. And then we try to assign that to a stock, but that doesn't work because count is not a subtype of stock. A variable of type stock can't hold a value of type count. And so the type system will report an error right here at the assignment statement. And you can see that this is actually a serious problem because it's made the inheritance of the increment method pretty useless. I can define new subclasses of stock, but I can never use the increment method on them, at least not without getting back something of the parent type. And so it's not as the inheritance of the increment method is not as useful as one might have hoped. So just to review, new stock, the incremented new stock will have dynamic type stock. That'll actually be a stock object that is returned. Okay, so don't get confused here. This is the dynamic type I'm talking about. So when we allocate the new stock object and then we call the increment method, remember the increment method returns self. So the increment method was implemented something like this. I'm going to leave out the types, but it was I gets I plus 1, and then it returned the self object. All right, so it's definitely returning whatever object is passed in here at the dispatch point. So it's returning something of dynamic type stock. And so this program will actually run, if you didn't have type checking, you could actually run this and it would work just fine. This would produce a dynamic stock object and it would store it into the stock variable. But it's not well typed because the type checker loses track of the fact that this is a stock object. All it knows is that increment is declared to have return type count. And which is certainly correct because every stock object is also a count object. It's just not useful in the context of this piece of code. And so the type checker loses information, which makes it not very pleasant to try to put the increment method in the count class to begin with. So to solve this problem, we're going to look at extending the type system. The insight is going to be that the increment method returns self. In this case, the increment method actually returns the self object. And therefore, the return value is going to have the same type as self, whatever self happens to be, which could be count or it could be any subtype of count. So the self object only has to be dynamically something that holds a value that's a subtype of the declared type of the self parameter. And so it could be any one of the subtypes, in this case, of the count class. And to do this, we're actually going to have to introduce a new keyword called self-type that is going to be used as the return, the type of the return value of such functions. And we're going to have to modify our typing rules to handle this new kind of type. So the idea behind self-type is that it's going to allow the type to change when ink is inherited, or allow us to reason about how the actual return type dynamically of the increment method changes when the increment method is inherited. So we change the declaration of ink to read as follows. We declare the return type now to be self-type, meaning the return value of the increment method has whatever type is the type of the original self parameter. And when we do that, now we can see that it's possible, we haven't said how we do it, but you should be able to see that it intuitively makes sense that we could prove facts of the following form. So when the self parameter has the type count, remember that the thing we dispatch to, the thing we call ink on, is the self parameter. So when we dispatch to a count object, we get back something of type count. And when we dispatch on a stock object, when we call increment on a stock object, well, what's the type of self? The type is stock, and we get back something of type stock. And now the program that we had before with this one change is well typed and would be accepted by the cool type system. Now, it's very important to remember that self-type is not a dynamic type. It is very much a static type and part of the static type system. It's also important to realize that self-type is not a class name. So unlike all the other static types in cool, it is not the name of a class. It's its own special thing, and we'll say more about exactly what it is in future videos. But the purpose of self-type, as we've seen, is to enable the type checker to accept more correct programs, and effectively what self-type does is to increase the expressive power of the type system.